Welcome to this video where we'll cover light in the electromagnetic spectrum. And the model we're working on today is light as an oscillating electromagnetic wave, so a wave. And what's important about waves? Well, the distance between two crests or two troughs, which is called the wavelength, and we can measure that in meters. We can also measure that in other units like nanometers, for example. The other thing that's important about light is frequency. A frequency of a wave defines that if we pick a certain point in space and we measure how often a light wave passes it, that's the frequency in hertz. So hertz, Hz, and seconds to the -1 are exactly the same unit. You're going to find that inverse seconds is the more useful unit. Other properties of light under the wave model are its amplitude, which is the distance that a crest or a trough goes off of the x-axis, so it's about its intensity. And then also its speed in a vacuum, and we can just assume that the speed of light is 3 × 10⁸ meters per second, so very fast moving. We do have evidence for the wave properties of light, and for a reference in your head, try to think about water, right? We know that water has waves, and think about what water waves do, and I want you to understand that light waves do the same thing. One thing that light does is refraction and dispersion, so when a wave, which has a specific speed, hits a different medium. So for light, this is like white light hitting a prism. The light traveling in the air changes the medium when it gets into the glass of the prism. The different waves that are inside of white light are bent at different angles and they move at different speeds, and so we get the separation of colors. So that white light actually inside of it had some blue and some green and some yellow and so on and so forth. That's a property of waves, and so that's evidence that light acts like a wave. The other thing that waves do, and this is really analogous to water waves, right, is that when they encounter an obstacle, they have to bend around that obstacle. It doesn't go through that obstacle. And that's called diffraction. And as a result of diffraction, as a result of going around the outside of an obstacle, you get interference where waves can either reinforce each other, and that's why these light waves are getting more intense in these different places. Waves can also cancel each other out, and that's why you have these dark spaces in between. This is where the light waves are negating each other. And both of these, again, are evidence that light acts like a wave. Because light acts like a wave, we get to say that its wavelength and frequency are related, and it's called a dispersion relationship. So because light diffracts, we have this refracts, we have this dispersion relationship going on, where the speed of a light wave, which is always 2.998, or about 3 × 10⁸ meters per second, note the units, that speed is equal to the wavelength, which we denote by the Greek letter lambda in meters, multiplied by its frequency, nu. That's the Greek letter nu. When I multiply those two things together, lambda nu, I will always get the speed of light, which means that I can go ahead and figure out, if I know two of these three things, which I always know the speed of light. So if I know its wavelength, I know its frequency. If I know its frequency, I know its wavelength. That's a very useful relationship for us. Before we solve our problems, I do want you to know that most of the time we're not going to be measuring our wavelengths in meters. We're probably going to be measuring them in micrometers, 10 to the -6, or nanometers, 10 to the -9. So I just want to take a moment to remind you about conversions. So for example, if I look on the bottom line of the conversion chart, I see that there's 10 to the -9 meters in 1 nanometer. And so I get to make conversion factors where I could either put the 10 to the -9 meters on the top and then 1 nanometer on the bottom, or do it in the reverse way. So again, I can use those conversion factors as I need. So for example, if I was given 650 nanometers, I'd multiply it by the conversion factor where meters are on the top and nanometers on the bottom so that I could cancel the nanometers, and I would find that 650 nanometers is 6.5 × 10 to the -7 meters. That's going to help me solve problems because, again, if we think about that dispersion relationship, I'm going to need my wavelength in meters and my frequency in seconds to the -1 in order to get the correct speed of light in the correct units. So because I can use that dispersion relationship, C equals lambda nu, and because I can convert things like nanometers into meters, I can now solve problems. So for example, I can calculate the frequency of light that has a wavelength of 650 nanometers. Again, I start with my dispersion relationship because the dispersion relationship takes wavelength and frequency and relates it to speed of light, which I always know. And Remember, I know the speed of light, 2.998 times 10 to the 8 meters per second. I know the wavelength, right? This is the one I had you convert in the last problem. And then nu is left as an unknown. If I have one unknown, I can solve for it. And I can find that the frequency of light that I'm looking at is 4.61 times 10 to the 14 hertz. Look how high that is. You notice how wavelengths are usually times 10 to the negative something or very small number of meters. Frequencies are generally quite large, right? They're at least 10 to the 6 hertz. They might be 10 to the 14. They might be 10 to the 19. So just to ballpark yourself, those are the kinds of things we're looking for. Let's try another one. Here's a known frequency, 1.6 times 10 to the positive 6 hertz. By the way, given metric conversions, we could call that 1.6 gigahertz, 1.6 GHz if we wanted to. But now, right, I know my speed of light still. I don't know my wavelength, but I know my frequency. And so I can solve for the missing frequency and solve for the missing wavelength and find that it's 187 meters, so fairly long. The last thing I want to make you aware of in this video is that there are many different types of light, flavors of light if you will, and they map onto what we call the electromagnetic spectrum. So what do we see? We see that at the top of the electromagnetic spectrum, there's the wavelength of light in meters, right? We're going to put longer wavelengths on the left and shorter wavelengths on the right. And the thing I like about this picture is that it maps you to the idea of how big something is, right? So if light has a wavelength of around 10 to 1 meters, the wavelength of that light is about the size of your house. By the way, these are radio waves, which is pretty good, right? That's how you transmit a long distance, use big waves. On the other hand, little waves like nanometers 10 to the negative 9 or picometers 10 to the negative 10 are around the size of a water molecule. And we've mapped the same idea in terms of frequency here, right? You notice the bigger frequencies go with the lower frequencies go with the bigger wavelengths and the higher frequencies go with the shorter wavelengths. If you think about the dispersion relationship, C equals lambda nu, that's why. If C is a constant, making lambda big has to make nu small. Making lambda small has to make nu big. And so that continuum of the electromagnetic spectrum is important because now we can map types of light onto that spectrum. So returning to those original problems, right, that 650 nanometer laser pointer, remember we decided that its frequency was 4.61 times 10 to the 14 hertz. And if I map that onto the electromagnetic spectrum, and this is just a slightly different way of expressing it, I see that 650 nanometers fits in this little tiny slice here that we call visible. Our second problem had us work on the wavelength of light with this frequency of 1.6 gigahertz. And if we map that, 1.6 gigahertz, remember, was 185 or 188 nanometers basically. So it's over here. We're dealing with radio waves, right? Radio and TV are down here. And so this is how we can map things to the spectrum so that we can use that information for later. It turns out that the type of light is related to the types of things that we can do to chemicals. So for example, radio waves do certain things to atoms. They change their magnetic moment just a little bit. On the other hand, when I use, say, X-ray light, I can actually take atoms and I can remove electrons from them and take them apart. If I use IR, I can vibrate molecules, right? Each different type of light has a different type of chemical significance, and that's one of the fun things about learning chemistry.